first one is a compact connected real group with Lie algebra SU2. So it's either SU2 or SO3. Well, since this group is simply connected, it's SU2, and then SL2R. So the real forms of SL2R is returning SU2 and SL2R.
I should note there is a substitute here.
Okay.
Type inner class with the Camel case, column G.
I'm sorry, inner class of G you'd like to know?
Yeah.
Camel case?
No, the column.
Huh?
The column G. Okay, so this is G can be implicitly converted to an inner class, and what you're really asking is the real forms of the class.
Yes, so Mark Mark's bringing up the point that when I said I'm getting the real forms of SL2, this is correct in this case. But in general, real forms are divided into inner classes. I'm going to talk about this in our lecture next time. And
No, but I mean, what you're asking, you're trying to say something. What are the children of X, and it's actually returning the children of the parent of X. And I mean, among these real forms, there is the real form itself.
Yes.
But it's strange that it's listed among its own children. But that's because it's implicitly converted to its parent.
Yes.
Class.
So, yes. So what I'm really asking is,
real forms of SL.
let's set IC to be the inner class of G. And then if you do real forms of IC, that's the really basic object.
And that was in fact what you were doing.
Yes. That's correct. Yes.
Is G PGI2R or SI2R?
In this case, it's SL2R.
Why is it disconnected real?
Oh, I'm sorry. What is G? Oh, I'm sorry. It's PGO2. You're right. So this is the disconnected one. So the two groups. So the two groups. Well, if you do real forms of PSL2R, you get PSL2R, which is disconnected. And what do you get here? Well, it's compact, and the compact form is always connected. And so it turns out that this is SO3.
Which looks nice if you write the second one as SO21.
Which is SU2 modulo plus or minus the identity. And if you think of this as SO21. Right. So they're groups, they're orthogonal groups with a signature of dimension 3. There's 2, 1 and 3, 0. Okay. So let's do a slightly bigger example. Let's say, take SP4R. What's its dimension?
That's the right first number of groups.
That's correct. Okay. What are its simple roots? So one of the nice things about Atlas is that for a classical group, like the symplectic group, it chooses the usual Bourbaki coordinates. So when we list simple roots and things like that, they're always columns. And so the two simple roots are 1 minus 1 and 0, 2. That's the standard simple roots for SP4. Okay? And what are the simple co-roots? Let's pause there for a second. So let's see. When you take the simple co-roots, the 0, 2 turns into 0, 1. Right? Suppose you want to know all of the roots. Well, can ask what are the
The positive is one more.
positive roots of G. G has 4 positive roots, the 2 simple roots, 1, 1, and 2, 0. One minus 1, 0, 2, 1, 1, and 2, 0. Those are the positive roots of SP4.
So draw 0, 2, 2 from the long root. It's hardly any higher than that.
You're right. Let's see. What are the real forms?
When you say that, you're implicitly comparing the root itself.
Tisk, tisk. So I find that a little hard to read, so I'm just going to do a little for loop. For H in real forms of G, do. So real forms of G is returning a list of real forms. And I'm just saying run over them and print them. So this just makes it look a little nicer. There's the compact connected real group with Lie algebra SP2. There's a connected real group with Lie algebra SP11 and SP4R. So the answer in this case is, I'm going to be using black. Black. The answer is SP4R, SP11, and SP2, which is also known as SP20, which is compact. So besides the split group and the compact group, there's one other group in between. Yes? The G's already what? Yeah, so the real forms command, this is what Mark was asking about before. Really, what I should have said is IC is the inner class of G. And this is a collection of real forms of a given complex group. So this says it's a complex reductive group, and it's a collection of 3 real forms, 3 dual real forms, but never mind. And when I ask for the real forms of SP4, I'm really asking for the real forms in the inner class of SP4, which is to say the real forms of SP4C, which is why I'm getting those 3 things. There's only one inner class. Yes, so let's do an example where there's not. Let's say SL4R.
Is there an easy way to enter an inner class? I mean, you could now say.
Yes. Yeah, so I could say, let's set IC to be the inner class of G. And so it says here, it's a complex reductive group of type A3, so that's SL4C. And it says, with an involution defining an inner class of type S. Well, I'm getting a little ahead of myself because I was going to talk about this tomorrow. But anyway, the S means that this is the inner class which has the split group in it. And so it has 2 real forms. So what are the 2 real forms of, what are all of the real forms of SL4C? Never mind inner forms, let's just talk about real forms.
SL4R.
No, let's just talk about real forms. What? Oh, SL4R is one, yes. What else? Well, there's the compact form. Every group has a compact form. What is the compact form of SL4C? Pardon me? SO4? What's the compact real form of SL4C? SU4, thank you. Which is to say, SU40. The unitary group on a complex vector space of dimension 4, preserving a Hermitian form of signature 40. So that tells you some other groups. SU31 and SU22. Any others? Quaternions. Thank you. SL2H. Okay, well,
Could you pause and tell us what the S means in SL2H?
no. Because I won't get it right.
Well, that's the reason I asked.
No, it's the real determinant. Anyway, okay, so this group over here, this inner class has two real forms. Never mind the dual guys. Two real forms. So let's see what they are.
Form names.
Form names
Form names.
of IC.
Strings that identify.
Oh, so this is like the last. This is the Lie algebra basically. If I do for A in IC,
They
do.
will construct the real forms themselves and they will do more information.
Oops. Oh, sorry, not.
Real forms.
Yeah, so Mark's pointing out that,
Oh, it's just another combination.
Yeah.
Just gives you identifying strings without the additional.
Right. yeah, so if I list the real forms, it's the connected yada, 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 and at the end here is the Lie algebra. And if you just do form names, you just get that Lie algebra at the end. So these two groups are being listed here. SL4R and SL2H. And the unitary groups are not appearing. And that's because they're in a different inner class. And let's set compact IC to be the inner class of A4.
A3.
So you put the root element of IC. So you say with the same root element of IC, and then with the
So now, this is a complex, it was still type A3, but it's an involution defining an inner class of type C. Now there are three real forms, and if you do form names of compact IC, we're getting these other three. So I'll explain this business about inner classes tomorrow, but that's, yeah. Yeah, so whenever you have an inner class, there's a naturally defined dual inner class, which is, so you start with a complex group, you have a dual group, and then the inner class gives you an inner class of the dual group, and it's telling you how many real forms there are in the inner class of the dual group. And the interesting thing is that in type A, these two classes get switched. The ICS is dual to this IC sub C. This is the one with SL4R and SL2H, and this is the one with the SU4031 and 22.
The statement at the top, I think, is true for AG.
Yes, that's correct. And I'm also glossing over the fact that this is really P. But anyway, so that's why there's different numbers of real forms on the two sides. So this notion of duality, that requires some explanation. It's sort of a refinement of just the duality of connected complex groups. Other questions? Yes?
The C at the end is for the compact.
This C in quotes?
Yes.
Yes, that stands for that means compact in a class. SP4? What about it? Sure. What is G now? G is SO4. So let's say G is SP4R. What would you like to see? Oh, the real forms? Okay. So let's do form names. Form names. Names of inner class of G. So this has three inner forms, SP4. So in general, SP2N, the real forms, so SP2NR, or SP2NC, has only one inner class. And the real forms are the split group, SP2NR, and the SPPQ, where P plus Q is equal to N. Yes?
Is there a code, pure real forms?
No, but I could write one. There is,
The information is
The-
printed out by something in Forco at least. I don't
Yeah.
remember whether it's easily available.
G,
What was the question?
pure inner forms. That doesn't look right.
How about,
Huh? Oh, no, I did sorry, H. That can't be right. Central invariance.
um,
Oh, wait, these are.
yeah.
That's not a good example.
For the SU.
So the answer to your question is, the pure inner forms are the ones whose central invariant is 0. So these are all pure inner forms.
If you do the SUPQs. Oh, you wrote central invariant of G.
Choose that too.
Oh, there we go. That's better. Good. We're not so. So SP4 has 3 real forms, and the only pure one is this one. What else would people like to see? Yes.
Sorry, a little bit lost. You were doing real forms, and all of a sudden you change it to form names, and they give different answers. What was going on?
No, the form names just gives shorter answers. So the form names is just telling you this Lie algebra at the end. So let me do this example. So G is SP4R. If you do for H in the real forms of G, you get 3 with all this information, connected, split, yada, 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 with Lie algebra SP4R. But if I do form names of inner class of G, I just get the Lie algebras at the end.
Also, just type what type of form names and what type of this just meant when it comes to a list of strings, and we do the same thing for the forms. And you see it will be linked class to a list of real forms. So it's not really the same thing.
Yeah. So, so let me do an example of that. Let's say IF to be the inner forms of the inner class of G. Oh, not IF. Set groups is equal to the inner form. Real forms. So this is 3 actual groups. And so, for example, I can take our set A is equal to groups bracket 0. A is an honest-to-goodness group that Alice can work with. It's the compact connected group Lie algebra SP2. It's a compact group. So the real forms command is actually returning a list of groups. The form names is just returning these strings, which is for convenience.
Who is missing on the board?
Here? No, that's SP20.
Oh.
So there's 2, 0, and 1, 1. Yeah, sorry, when
Also, PQ and QP is the same.
PQ and QP are the same, correct?
What was the various command you used?
It's called central invariant. It's getting a little bit ahead of ourselves, but since someone asked, let's do what type? So it takes a real form to an integer. So let's do the following. This is something we haven't shown you yet. Let's do central invariant at real form. So this is a new syntax. This says take the central invariant function. There's a central invariant function. There are 2 versions of it. One which takes a pair like this, one which goes like this. This is the one I'm interested in. So, but when I say at real form here, I mean I'm talking about the version of this function which returns an integer. And when I give this syntax, what this is going to do is it's going to tell me how the function is defined. And it's this syntax that Mark mentioned that's been parsed and it's almost impossible to read. Find, well, whatever. But if you want to read about it, what you should do is you should go to this file at line 62 and see what it says. So let's do that. Because what's written here is the interpreter's condensed version of what's written at line 62 in this file. And if we're lucky, the author of that file put in a comment explaining what it does. I'm going out on a limb here.
The one thing that this form is not very readable, but it will help you identify if the definition itself uses overloaded function, it will tell you which overloaded version it's using.
Absolutely. Yeah, you can extract useful information from this. Set, what was it called? Central. Associated to a real form is an element
The one you were talking about.
oh, sorry,
So that-
it's the next one. Well, they're both explained by this text up here. And what this says is that if you have a real form, associated to a real form data, is an element of the center. Well, actually, this subquotient of the center, z up with theta modulo 1 plus theta z. And it's some Galois homology construction. And here's an explanation of how it's found.
Where are they?
What are they good for? Well, someone asked about them, that's all.
Actually, the comment is talking about this before.
It is. Isn't that
More
interesting?
than enough.
What's that?
More than
More than you asked for, that's right.
It says something here, it doesn't say what it means.
That's true.
The second line of the comment more or less says, you take the Cartan, you take the, basically there's some group element that represents the Cartesian evolution. You square that group element, you get something in the center, because it's a quality of automorphism. And so that's the central invariant. It's a class in the center, and well, the choice of representative of the Cartesian evolution, there are various choices to make, and so the central thing you get isn't really well defined. It's only well defined.
Right. Okay, let's do another example. I could, well, let me do one more structure theory example, and then I'll do a little bit of representation there. So let's set G is equal to E8. And I'm going to pause here and I say, okay, I'd like to define a real form of E8. How do I do that? Well, it beats me. So I'm just going to type E8 tab and see what happens.
Can you remove the second ring?
And this really bothers you, Mark, huh?
I just don't want to get that.
So I hit tab, and I saw all of the completions of E8. Now, these are various things. The E8 elliptic regular is something having to do with log elements and so on. But there's an E8, there's an E8C, there's an E8IC, there's an E8Q, and there's an E8S. And I'm going to guess that E8S is probably the split form of E8. And E8C is the compact form. And E8Q is this other mysterious quaternionic form. And that's correct. So let's set G is equal to E8S. Oh, G colon.
What type of S? What question was?
Oh, this is this crazy.
Yeah. This is because E8 is so big.
Yeah.
Construct
Terrible example. Okay. Let's G colon equals split. So there's just one crazy little thing here. And actually, we should get rid of this because it's so much faster now. When 10 years ago, when we first wrote this, if you loaded the groups file, it loaded all these different definitions of the groups, the exceptional groups, and the E8 really took a long time. And most of the time, you weren't asking about E8, so you had to sit there for 2 minutes while the software loaded, just to load this stuff about E8 that you didn't care about. And so Mark put in this very clever thing that it doesn't actually initialize it until you need it, which is what's tripping us up here. But things are so fast now that it shouldn't matter, right? Anyway.
It happens every time we start a
Yeah, that's true. All right, anyway, here's the split form of E8. Connected split real group with Lie algebra E8 to R, meaning the R means the split form. What are the simple roots?
So you decided to get that from a different group.
Huh?
Well, you have this command that you execute.
Oh yeah, so I had a different command. For any root system, you can take the split form. So let me, sorry, what type E8? E8 is a string. E8 is just shorthand for the string E8. Okay? What type split form? Split form takes various things and gives you back a real form. And then there's some implicit conversion, which does it. Anyway, split form of the A works. Okay. What are the simple roots? So remember, the simple roots are the columns, and there they are. So they're not the simple roots in Bourbaki notation. Bourbaki, the simple roots, some of them have halves in them. And the Atlas is software. One of the basic things it does, and I'm going to talk about this tomorrow, is it picks a basis of the character lattice of T and makes it isomorphic to Zn. And in particular, the roots are all integral vectors. So it's
simple co-roots of G?
that's an interesting question. What are the simple co-roots of G? Anybody? It still can't have still can't have half integers. It's still going to be an integral matrix. So this is this.
No, it's not. No, it's not. Well, it depends.
Well, it depends how you define it.
Yeah.
If you're the sharp-eyed people in the audience recognize this matrix as the Cartan matrix for E8, and a basic property of root data is that if you take the simple root matrix, I think it's the transpose of this matrix times that matrix, you get the Cartan matrix. So, for example,
Actually, you get transpose. That's just
sorry, what? It is the identity matrix. So, well, again, I'm getting a little bit ahead of myself, but why not? We have this group G, and we have a Cartan subgroup H, and we have X upper star of H, and we have X lower star of H. This is the character lattice. This is isomorphic to Zn. This is the co-character lattice, is also isomorphic to Zn, where n is the rank. And there's a perfect pairing between these. So that's the abstract mathematics. Now, the software is choosing a basis.
due to the lower star of that.
I'm sorry, what?
The last line,
The last one,
the lower.
exchange the stars. Because I would.
Oh, in the other order? I understand, yeah.
It's just as perfect.
So this is mathematics, all abstract. The software